BMV, Bergens Mekaniske Verksteder AS, is a holding company for the following group of companies: BMV Engineering AS, BMV Laksevåg AS, BMV Bergen Contracting AS, Bergen Jernstøperi AS, Hydrovinch AS, and BMV Machine AS. BMV Machine AS is located near Norway's second largest city, Bergen. The plant itself is located at Hordvikneset, some 20 kilometers to the north of the city of Bergen. The modern installation was established in the period between 1968 and 1972. The site itself covers approximately 50 acres, with approximately 10 acres presently being utilized. The plant is ideally positioned on the coast, and the quay is arranged to accommodate vessels up to 7,000 tons dead weight. The crane on the quay has a lifting capacity of 90 tons safety workload. The company is well known in the marine and offshore industry for its design and production of diesel engines and hydraulically powered deck machinery. The company employs approximately 800 people. 350 of these are skilled workers engaged in numerically controlled machining, mechanical assembly, quality control, testing, service, and welding. The company also has 150 engineers engaged in design and research. To ensure optimum coordination, BMV has implemented project management techniques as part of its managing systems. BMV Machine utilizes several large computer installations. This is the largest installation with BMV Machine at Hordvikneset and is utilized primarily in connection with computer-aided design, manufacturing, and materials control. The use of computer-based systems in both the office and the plant is of primary importance to a company of BMV's size. The Quality Control Department has an authoritative function in the assurance that specified quality requirements are maintained at all levels in the organization. There is a steadily increasing use of computer-aided design in product design. This provides flexibility and ensures satisfactory utilization of capacity in the design departments. Alternative designs can be quickly compared, and changes in design are much easier to accommodate than with previous traditional practice. The utilization of the finite element method assists in the calculation of theoretical stresses and deformation in proposed designs. This provides the opportunity to obtain optimum design solutions. An important aspect is the very high speed of these calculations, enabling alternatives to be evaluated in a very short time. The solutions arrived at with the help of finite element analyses in the initial theoretical evaluation can eventually be compared with actual measurements taken at the completion and test of the equipment involved. This provides engineers with the opportunity of actual experience with utilization of computer-based models for obtaining optimum design and performance of the equipment. Computer-based models are also utilized for the calculation of frequency response, torsional vibration calculations, linear and nonlinear dynamic systems, and stability analyses of speed governing. Computer-based systems within material and production control ensure optimal stock control and capacity utilization. The MPS system provides quick and reliable information regarding available technical resources. BMV machine uses numerically controlled machinery for approximately 60% of its machining. CAD-generated drawings give the basis for the development of programs employed in the control of numerically controlled machines. APT, Automatic Programming Tool, is utilized. This is an advanced computer language especially developed for a rational description of operations and tool paths in numerically controlled tooling machines. Through the application of a post-processor, the APT program is translated to the individual control languages. Computer-aided manufacturing gives optimum machining data and a graphic verification of the tool paths. The movements of the tools are simulated by the computer. The completed programs are entered into the individual machine's control units. This ensures completion of the defined tool path with very high precision. Complementary components are ensured a corresponding dimension without the use of jigs. This machine picks up the blank parts from the component station and delivers the parts forward to the machining area for location in machining position. This machine is numerically controlled and designed to check the dimensions of the machined components. The machine registers any discrepancy from the defined tolerance and corrects for tool wear and other causes of possible tolerance discrepancy. NC machines require tool presetting. In this operation, precise checking is of importance. At the computer numerical control measuring machine, the dimensions of the products are checked with high precision. Any measurement discrepancy is presented both on a screen and at the printer. This ensures that any dimensional discrepancies may be corrected. A modern shop blasting installation can clean products of up to the following sizes. The largest diameter, 2,850 millimeters, and maximum height, 4,669 millimeters. Cleaning effect corresponds to SA 2.5. The company has solid traditions in the assembly of precision products, such as diesel engines and hydraulic equipment. Personnel are used to working with fine tolerances and under strict requirements for cleanliness during assembly and testing of the equipment. Trained, skilled workers are able to meet the relevant quality assurance specifications and requirements. All products are tested in simulated operational conditions in accordance with quality control requirements. Documentation from these tests is supplied with the product. The company utilizes computer-based measuring procedures in connection with product development in diesel engine design and hydraulic equipment design. Since 1976, special computers have been in use for acquisition, processing, analysis, and presentation of measured data. This computerized equipment has been updated continually in line with developments in this field. The system can handle static and dynamic measurements and includes comprehensive information on most physical parameters. An example is the wireless transmission of signals for moving parts within an engine, that is, crankshaft, pistons, etc., with an acquisition frequency of up to 50 kilohertz. Similar testing and measuring processes undertaken in the field outside the plant are normally recorded on a multi-channel tape recorder for later playback for further processing in the computer.